Well, the last talk today will be given by Dr. Palmadesso. It's entitled Anomalous Resistivity in Magnetosphere-Ionosphere Current Systems, the Role of Ion Cyclotron Turbulence.
Of all the mechanisms which have been suggested to account for the anomalous resistivity postulated in field-aligned magnetosphere-ionosphere current systems, perhaps the simplest are those which depend upon current-driven instabilities. Kindell and Kennel, in a paper published in JGR in 1971, calculated threshold values for the relative electron-ion drift velocities that one would need to excite various instabilities in the ionosphere or magnetosphere. Of all the instabilities studied by Kindell and Kennel, the one with the lowest threshold was the electrostatic ion cyclotron mode. And this, therefore, would be the first mode to be excited by a field-aligned current. The obvious, but not trivial, next step is to estimate the magnitude of the resistivity and the associated IR drops that can be produced by this mechanism. And this is the goal of the work that I will describe today. Before getting to the details, let me summarize, just to hint at our conclusions. It appears at this point that ion cyclotron turbulence may lead to some enhancement of the resistivity over its classical value. But we don't feel at the present point that one can get very large enhancements in the resistivities. However, cyclotron turbulence may, in some circumstances, play a role in determining the ambient ion temperature at high altitudes. Well, before we can actually go into a calculation of the resistivity, to estimate the resistivity, we need to say something about the parameters of the ionosphere. And there's a complication here. We can, for example, make some statements or make some estimates of what we think the temperatures, etc., might be in the ionosphere and magnetosphere, and then calculate a resistivity on the basis of those assumptions. But now, once we have a resistivity and a current flowing through this anomalous resistor, we get heat dissipation, and this is in the nature of this particular mode that most of this energy goes into the ions, and this can change the temperature of the ions from what one would guess it to be on the basis of the background outside of a field-aligned current. The simplest way to approach the thing conceptually is by an iterative procedure. That is to say, we make some assumptions about temperatures. We estimate what the resistivity is going to be. We estimate the heating rate from that, and then change our guesses as to what the temperature will be, and then iterate the thing over again. So I'll proceed along those lines. We'll consider a simple model in which we have a field-aligned current carried by upward-moving electrons. We'll consider a pure hydrogen plasma, since the instability that I'm talking about occurs primarily at fairly high altitudes, in which there is mostly hydrogen. And for simplicity, I'll start by assuming that the electron and ion temperatures are equal, and I'll pick the number 2600 degrees. Well, upward flowing current here means really upward flowing electrons. We characterize the resistivity by an effective collision frequency. And this depends upon the imaginary part of the electron dielectric function, which depends upon the parameters of the plasma. And also, the effective collision rate is proportional to the level of turbulence that one has, the fluctuation energy of the fields. There are various factors which depend upon the saturated level of these fluctuating fields. I won't go into the details of this calculation because time is limited. We've essentially made a very conservative, taken the most conservative assumptions about the rate at which the turbulence grows with altitude above the threshold point. And then we've assumed that the final saturation occurs by ion resonance broadening. And Dum and Dupree have done a calculation of what magnitudes of fluctuations you get, assuming that this is the correct mechanism. Well, we need to say a few more things about the parameters of the ionosphere and magnetosphere to actually get some numbers out of this. In particular, we need to know what the drift velocities are as a function of altitude, and what the currents are, and densities, and so on. So I'll consider three density profiles. These are taken from the paper by Kindell and Kennel. The middle one is a quiet auroral profile. It's an extrapolation of a Rees and Walker profile. Number one is a trough profile, and three is a disturbed auroral condition. So we sort of bracket reasonable parameters. And we'll consider three different flux densities, 10 to the 9th, 10th, and 11th particles per centimeter per second at 200 kilometers in the flux tube. This is a typical result. This is for the case of profile number 2, which is a quiet auroral profile, and the intermediate flux of 10 to the 10th particles per centimeter. The instability gets started when the electron drift velocity is about a third of the electron thermal velocity. And we find that this is, here I'm plotting delta R, which is the resistance per kilometer of tube length. The resistance increases rather rapidly and then peaks out, and it goes down because the magnetic field is decreasing with altitude and the saturation level of the turbulence is sensitive to the level of the magnetic field. For this particular case, we get a value of about 1.2 kilovolts for the total potential drop that one would get for this resistance and this current. Here we've summarized a number of different cases using the different profiles and the different fluxes. The important thing to note here is simply that the IR drops that one gets are around the kilovolt range, 1 kilovolt range typically. Well, the next thing we have to do is decide what this is going to do to the ionosphere. It's a fairly simple matter to do this. We know what the IR drop is, we know what the current is in each of the various cases, so we can calculate a power dissipation, which is just IV, or J dot E, if you will. And so we know what the total energy being dumped into the ions per second. You divide by the number of ions. And it turns out that for kilovolt potential drops, such as we have here, spread out over distances of the order of 5 or 10,000 kilometers, 5, 6, 12,000 kilometers in this case, each ion would have to absorb an energy of about, well, several electron volts per second. And since the thermal velocity of the ions is typically less than 1 electron volt, it's very hard to see how this can happen without rapidly heating up the ions. By any reasonable estimate of the heat conduction rate, the rate at which the ions can conduct away this heat, it seems that the rate of absorption is orders of magnitude above the rate at which the ions can get rid of the heat. So, therefore, there's something wrong with these estimates. We can't simply stop here. Well, what happens next? What is going to happen? The most reasonable, the simplest explanation is simply that the ions do heat up once we get the instability started and once we have the field-aligned current going. And it turns out that the instability is sensitive to the ion temperature, the growth rates of the instability. And the critical drift velocity needed to excite the instability increases as we increase the ion temperature relative to the electron temperature. So what's going to happen then if we heat the ions without simultaneously heating the electrons, which is what we expect to happen, is that the instability is ultimately going to shut off at some ion temperature. In other words, in the final equilibrium, we expect to have a situation where the instability, the growth rates of the instability are reduced sufficiently so that the heating rate is just equal to the rate at which the ions can conduct this heat away. And since the heat conduction rate for the ions is very, very small, we expect that the final IR drops that we're going to get out of this will have to be very much smaller, 2 or 3 orders of magnitude smaller at least, than these potentials I have here. And that means that the resistivities are going to be correspondingly smaller. The temperature business is an interesting point. With this idea that I just mentioned, that is that in the final equilibrium, the heating rate is balanced by the conduction rate. We feel that the final state will have to be very close to a marginal stability state for the turbulence. And using that idea, we can calculate a temperature profile in the final state. We started by assuming that we had electron and ion temperatures equal and around 2600 degrees. And what we think will happen was that the ions will simply heat up until the critical drift velocity at each altitude is equal to the actual drift velocity, or very close to the actual drift velocity. And for that intermediate case that I showed you before with the quadroll profile and 10 to the 10th particles per centimeter, you wind up with an ion temperature profile which looks something like this. We start around at the onset of the instability with about 2600 degrees, and the thing builds up to about 10,000 degrees. I should point out at this point that the particular height and shape of this profile depends somewhat on the electron temperature that I assume initially. If, for example, I were to assume a higher electron temperature, say twice what I assumed actually, I would have to settle out at much higher ion temperatures. I might get up to 20,000 degrees instead of 10,000 degrees. Also, we haven't considered any other processes which might be going on which might also be heating up the ions. If something else were happening that would heat up the ions, for example, suppose the ions were 5,000 degrees to start with instead of 2,600 degrees, then we'd be starting around here, and the instability just wouldn't start until you cross this line, which is essentially the marginal stability line. So, in conclusion, in summary, we think that one probably can't get kilovolt potentials from ion cyclotron turbulence. You can't get rid of the heat dissipation that's implied by such potentials, and the heating, if not dissipated, essentially kills the instability. But as a consequence of this, one can expect changes in the ion temperature profile at high altitudes. And unless there are other heating processes around which drive the temperatures above those that I predicted here, one might be able to look for and actually find such temperatures and see the effect of the turbulence. Thank you.
First, a comment. The preliminary data from ISIS seem to indicate that at high latitudes where the field-aligned currents have been observed, up to 3,000 kilometers is dominated by O+ rather than by hydrogen. And I wondered if that affected your calculation
Well,
significantly.
if you notice, for example, on this slide, the instability that I'm talking about, the ion cyclotron instability, doesn't get started till around 3,000 kilometers. And it goes up to, in this case, about 8,000 kilometers. Or typically it'll get started at a few thousand kilometers and go up to maybe 10 or 15,000 kilometers. At those altitudes, you have mostly hydrogen. When we got started with this thing, we were mostly interested in the resistivity, trying to calculate the total resistivity. And since that's what one really wants to look at is the path-integrated resistivity, and since we expect it to be spread out over 10 or 15,000 kilometers, the first 2,000 or 3,000 kilometers aren't going to make a whole lot of difference. And so we just consider the higher altitudes. If one wanted to look for this heating effect, the adjustment in the temperature profiles that I mentioned at the end, then one would want to consider oxygen, because the heating effect is essentially a local effect, and if anything, one would want to be more interested in lower altitudes where it would be more easily measurable. And at those altitudes, hydrogen certainly would be important, but we haven't yet done that.
Could we go back to the previous slide, please? The one showing the, yes, those the different combinations. The bottom line in each box, is that the thickness? The delta A, is that the kilometer altitude over which the resistivity is distributed?
Yes, that's right.
Okay, that seems to be very much larger than tens or even hundreds of Debye lengths, and that could be a way of distinguishing this type of anomalous resistivity between double layers, which are much thinner. Could you comment on that, please?
Well, yes, I would expect to see this the turbulence distributed over over long distances. It wouldn't be confined in little pulses or bursts. It's distributed over long distances, and it'd be the gradients in the resistivity would change slowly over those distances.
Okay, thank you.
In your calculation, magnetic field doesn't enter, but the expression is actually along the line of force, isn't it?
Yes, everything is happening along the line of force. So, I mean, I haven't gotten into the details of the calculations, but things are sensitive to the magnetic field strength and so on, and I've considered those effects.
Okay. I wonder if it's worth considering, I'd like your opinion on whether it's worth considering the ion cyclotron instability at lower altitudes. I presume you cut off at 3,000 kilometers just because the density is going up and the drift velocity is going down. On the other hand, at the lower altitudes, the heat dissipation mechanisms are increasing rapidly. Could you comment on the likelihood of getting large IR drops below a few thousand kilometers?
Well, Kendall and Kennel did quite a bit of work on deciding where the thresholds, when you would exceed the threshold and so on, based on various density profiles and various assumptions about the flux. And in one case, for one set of conditions, they were able to get the threshold they were considering an oxygen mode in that case, down to about 400 kilometers. But this is sort of an extreme condition. Typically, you expect the thing to start, even considering oxygen, which they did. They considered not just hydrogen, as I did. But for the more typical cases, one would expect not to see anything below about 1,000 kilometers. And so I would think it unlikely to see high R drops due to this effect at very low altitudes. Of course, if you could get the thing going at very low altitudes, then that would help you out with this heating problem, because if you have lots of neutrals around and so on, you can dissipate the heat more efficiently. But that's hard to do, it turns out.
I think it's important to view this particular problem in the context of other plasma flow problems at high latitudes. And yesterday I showed some results of self-consistent computations for ambipolar flows, where on these particular field tubes, whether in the polar cap or in the auroral oval or even south of that, the equatorward of that, one finds that you can have temperatures up to 9 to 15,000 degrees very easily. What you're imposing now on a system of coupled O plus H plus is an additional energy dissipation, perhaps what Keith Cole called a true Joule dissipation, and you're expecting the ions to react in some self-consistent fashion with this. It isn't possible just to equate the rate of this heating to ion thermal conduction downwards into the atmosphere, because the protons themselves are going to be accelerated outwards and enhance any polar wind flow that's going on. So I think the computations you've done are probably a little naive, and I would suspect that what this is going to do, the energy is going to be carried away as kinetic energy of the particles, the protons themselves. I don't say particular energy balance. This is something in the context of having a current flowing through a system that's already extremely dynamic, that's already with temperature levels such 10,000 degrees should not be uncommon. I should also point out that there are these measurements now from the Goddard group, Gene Mayer and other people, which show very elevated proton temperatures over O plus temperatures. And I think more experimental data like this should be examined to just find out the thermal balance and its relationship to the chemistry and the overall system, rather than just trying to pick out individual terms and equate them.
It is a complicated problem. I have not yet made numerical estimates of the heat conduction rate of the ions, except to mention, as I did before, that we realize that it's going to be very small. It's a slow process, and therefore if one does have an instability in the turbulence, that one is going to get heating, and one is not going to be able to conduct it away very quickly. That's as far as I've gone so far. I do recognize that it is a complicated problem. As far as the other business with the 9 to 15,000 degrees generated by this other heating process, we did not consider that. We were not aware of it. I hadn't thought too much about it while we were doing this calculation. If you do get heating by that or some other process above so that the temperatures wind up above the temperatures that I'm talking about here, then one just doesn't get the instability at all. On the other hand, I think by considering other parameters, I've only considered one particular electron temperature here. One might require higher ion temperatures to shut off the instability than 9 or 10,000 degrees. It depends upon the individual case. In some cases, I believe there probably will be some cases in which the turbulence does get started. But again, what we expect to get out of this is not really a resistivity so much as possibly a local heating event.
Well, I think the point is that just in the purely ambipolar case, this is happening anyway, and you're just adding one more heat source of about the same order of magnitude, and it's going to be soaked up very quickly.
I think we better just have one last comment, otherwise
Just want to ask if these effects are not very dependent on the local number density or the local concentration of ions. And this is going to be, I would imagine, upset considerably by the processes you're talking about. And is that the reason, too? Is it the concentration level that keeps these things at high altitudes? You said you can't do them below 1,000. Is that dependent on the number density?
No, not really. The instability turns out to be very insensitive to the number density. It's the drift velocity that's really controlling it. The point is, well, in a sense, the number density comes in. It's important in that it determines the drift velocity. You start out with a flux at some low altitude. You have to conserve flux in the flux tube as you go up. The density is decreasing, and therefore the drift velocity has to increase. And it's the threshold condition is a condition on the drift velocity and not on the density. I've considered several cases with widely varying densities. I showed you those three profiles: the trough condition, the quiet aurora profile, and the disturbed aurora, and they vary. Each one differs by about an order of magnitude. So the calculations span about 2 orders of magnitude in density. But if you then match the flux in such a way, choose a flux corresponding to each density profile in such a way that you get a reasonable drift velocity profile of drift velocity with altitude, then it turns out you see about the same thing. For example, here I've considered the quiet profile on a flux of 10 to the 10th. Here's another slide which I didn't get to show. Here we've assumed the trough profile with densities of about an order of magnitude smaller, and I've correspondingly reduced the flux, and as you can see, the curves are about the same because the drift velocity profile turns out to be about the same. And one more case where we have a disturbed auroral condition with densities 10 times higher than the ones I mentioned in the first one, and correspondingly higher fluxes, and again you see the same sort of behavior. So it's not really the density that's important.